CRISPR and breeding go together.
Yeah.
It's a hand-in-hand thing. And what CRISPR allows you to do is make the changes that you really wanted to make, but you would have to make massive populations to get with traditional breeding. So that's why they go well together. So you can think about traits that I really want this one thing, but I've got 30,000 genes segregating when I do a cross. Now I can just fix that one difference, and that's something that was never available with traditional breeding, but together they become really powerful. The way that we think about it is there are some traits that are very complex and involve lots and lots of genes.
Yes.
And those are probably the ones, at least at this stage of CRISPR and the cost of deploying it, it's better to just use traditional breeding.
Yeah. So all of the big players, Syngenta, Corteva, so on, have got gene editing programs, and then there's firms such as yourself and Tropic and so on. Is everyone deploying slightly different tools? How do you see the landscape evolving?
Yeah, so the tools themselves, I think we all have different levels of experience with the tools. I think we're very lucky at Pairwise because of our big partnerships that we've probably done more crops and more edits than really just about anyone. So there's kind of three types of editing. There's one that's now, even though it's only 10 years ago that we started doing this, that we can call conventional editing, which is what's always depicted as scissors. And that's Cas9, Cas12, and we have a version of our own that we call Shark that does that kind of scissor cutting. We, from very early on, got quite interested because one of our co-founders invented what's called base editing. So that became something that we put a lot of effort into, which is, if you think about using your delete function in an editing, I guess to use the bad metaphor, base editing is more like a search and replace. So you could take a word, like a misspelled word, like say it's the worst of times spelled W-U-R-S-T, and turn it into it was the worst of times by changing the U to an O. So base editing allows us to make those tweaks, and most of the genetic variation in plants is tweaks. It's not presence absence. So we're quite good at that. And then there's a third form that's called template. We call templated editing. One version, again, one of our co-founders invented, is called prime editing. We've got a version of that we've created that we call redraw that allows you to change the whole word all at once. So rather than just changing worst to worst, we can change worst to best, for instance. So one of the things in our initial Bayer collaboration, we wanted to make a bigger ear, and it turns out that there's a few genes that have been understood that determine the number of rows of kernels in an ear of corn. And those were found by maize geneticists years ago, and basically a loss of function mutation, which you can create easily with the scissors, with the first version. You lose control of number of rows and it just becomes this big softball, it's unharvestable. But we were able to identify certain amino acids within that protein that we thought were important. So using base editing, we made what's called an allelic series. So we made different mutations in the same amino acid to turn it into several different ones. And normally an ear of corn would have 16 rows. We made plants with 18, 20, 22, 24. So we could actually then take those different sized ears and test them in the field to see which ones were best. And it turns out that 16 is probably not best. You can probably get a little bit higher yield with higher numbers. In general, we're creating, we're a technology company, so we create different genetics. In some cases, we start with our own varieties that we acquire, like we did with our leafy greens, where we took mustard greens that were publicly available and we removed the mustard flavor from them, or the wasabi taste from them. So in that case, we have licensed the outcome of that to Bayer's Vegetable Group, where they can sell them and we'll get a royalty on that. In other cases, we have a partner that's committed from the beginning that helps to fund the production of the traits, like our Bayer and Corteva relationships. And they'll develop those products. It's pretty unique that we actually get to work with the elite germplasm of both Bayer and Corteva. I was realizing that I think we might be the only place in the world where both the elite germplasm from each of those is being worked on in the same laboratory. So we get to work with their elite germplasm and it goes into their pipeline. They'll develop it, and again, we'll get some royalty based on the value that we were able to create for them. And then other places like the work that we've done in blackberry are sort of in between what I described for the greens, where we're we've developed a product, and we'll be working really a model a little bit like say a Sunworld does with their grapes, where we'll license the germplasm to growers and then share in the value of the product that gets produced.
Are there any other projects that you're working on, either internally or in partnerships, that you can mention?
One that I'm very excited about, and I mentioned the seedless blackberry, which I'll say a little bit about, but we started with the idea of a pitless cherry, and not just to make it pitless, but actually to change the architecture and make it so it can be grown in more environments, so we could have cherries year-round that don't have pits. So we're really just at the early stages of that, but we've now created a system that we can do editing in cherries. We actually made a cherry tree that flowers 5 months after you plant the seed, which is normally would take like 5 years. So it's a little too early. We need to tweak it still some, but it's I think it's a very exciting opportunity to move into all these fruits and make them more palatable to people. And we started, as I mentioned, we made a seedless blackberry, which we've just recently got it to the point where we're actually getting the blackberries without the seeds and can eat them. And I'm one of the few people who's gotten to experience this. And I was a little skeptical of how big a difference it would make to not have a seed in a blackberry, but it's like a seedless grape versus a seeded grape. It's really different to eat a seedless grape, and it's the same with the blackberry. It's just this burst of flavor without the grittiness, and I was really amazed. So I'm looking forward to everybody being able to eat them.
So when you say seedless, it's still got a seed, but it's edible. It's not like
seedless grapes have seeds as well.
Sure.
And in fact, what we're just doing the studies, but my expectation is they will be more nutritious than a normal blackberry, because the seed often contains the nutritional quality, because blackberry seeds are actually pits, they're not seeds, so they're covered with this hard coat. You never get that nutritional value from them. So we've opened up the fiber and nutrition that's present in the seed.
I mean, generally speaking, where do you see this technology going? Because of the speed and precision and perhaps the smoother regulatory pathway, is this going to unlock a lot more exciting work in the plant breeding space?
Yeah, I think, and you talk about the smoother regulatory pathway, there's still some smoothing to go on.
Okay.
And I think we've approached it, and the world has approached it as, again, recognizing that the things that we accomplish with gene editing could be accomplished with breeding, and we should treat the products, it should be about regulating the product, not the process.
Yes.
And if the product was something I could have got with breeding, then I shouldn't have to test it any differently than I would something breeding. I think we're still at the early stages of that, and we're all hoping that Europe's going to come along and agree, which will really make a difference. That's going to, once the globe has really agreed on a regulatory system, it's going to really accelerate the ability to deploy things.
But are there still some applications where, if you want to achieve the benefit, you really need to do genetic modification?
Yeah. I think there's potential for things like insect control with gene editing, but there isn't that much natural resistance to insects, so really trying to improve on that with just the native genes is probably still, we're a ways away from understanding how to do that. So in those cases, the power of BT genes and other approaches that have been used for insects. On the other side, we've never really found a transgenic solution for disease, and we are seeing some really interesting progress on disease control using gene editing. So for instance, we did something in our Bayer collaboration where we created a soybean that's tolerant to the Asian soy rust. And still see whether it gets all the way to be a product, but it's looking really good in terms of its performance in the presence of disease. And we're able to essentially change the host in a way that it doesn't respond the same way to it. So it's different than the types of resistances that people breed for, and I think will be more robust because it falls into this category of non-host resistance, which is pretty intriguing.